Okay, so let's start with this example. Okay, so this is just an example to illustrate one way to bring arc length into the whole realm of things, but we'll talk about a general approach. This is something that we can figure out right now based off previous knowledge. So for example, this is a what shape? What is the parametric equation for a circle? Cosine t sine t. Where do I put the radius? There we go. Okay, so we've seen these before. Now, with circles, let's just draw a picture. When we write the parametric equation, we use this angle with respect to the positive x-axis as our parameter. Here's our radius. What is this piece here? That's the arc length. So let's call that S. Okay. Now we already have the required direction in this parameterization. This is the usual parameterization. If we reverse the cosine and sine, then that switches the way that we rotate. And our initial point, if you plug in 0, is already lined up to A0. The only thing is we need to find a way to, instead of use t as the parameter, we want to use s. The arc length. Do you guys remember when you first learned what a radian was? You probably talked about this formula. This would have been, what, sophomore year for most of you? Do you remember, Dave? Alex? AT. Yeah, that's exactly right. Good. So, you probably saw it as S equals R theta. Wow, that is a horrible theta. Let's try that again. S equals R theta is what you're used to. Here we're just using the correct variables, okay? So in this case, T would be A over S. Or I'm sorry, S over A. So now we have a way to replace the parameter, which is currently the angle T here. Now we're using the arc length parameter. Okay, so our new parameterization would be a function in terms of S, and we just replace T with S over A. right. Any questions on this example? Now, you don't really, if you didn't remember that formula, it's not a big deal. We're going to be interested more with the general change, and then there's going to be a method that we can use to find an arc length parameter for any vector valued function. So we'll talk about those. Okay. So let's just talk about a change in parameter in general. In a vector valued function, a change in parameter is a substitution, let's say t is going to equal a new function, g of tau, that produces a new vector valued function, which would be r of, instead of t, now we'd have r of g of tau. That has the same graph as r of t, but is traced differently as tau increases. Okay, so an arc length parameter is one example. You could also be given a set of conditions that you want to meet. So for example, let's say we have the vector valued function r of t equals cosine t sine t, so another circle. And let's do a couple of things. Let's find a change in parameter. Bless you. So circle is traced counterclockwise as tau increases over the interval from 0 to 1 as t increases from 0 to 2 pi. Okay, so we've already talked about the circle. Okay, so currently, as we range the angle from 0 to 2 pi, when we're at 0, we start at the reference point, which in this case was a0. As the angle increases, we just go around the circle, and as we finish and end up when we started, we're back at 2 pi. Does that make sense? Okay? So here, for whatever reason, saying, you know what, we don't like being in radians, let's just, maybe this is revolutions. Does that make sense? So instead of 2 pi, this parameter would indicate how many revolutions we've gone in terms of going around the circle. Does that make sense? So let's see what that would entail. What kind of relationship do we expect if tau is increasing from 0 to 1 at the same time t is increasing from 0 to 2 pi? What's that? Yeah, they're proportional. So we can just set up an axis here. Let's say this is tau. let's say this is t. When tau is 0, we want t to also be 0. When tau is 1, we want t to be 2 pi. Okay, so now we have a nice little linear segment that we could use to figure out the relationship. What would the equation be that relates t and tau here? Oh, by the way, I forgot something. This should be when tau is 1, t is 2 pi. I forgot to label that. Okay. So what's the equation between t and tau? 2 pi tau. Good. It's just a linear relationship. Okay, so then r of g of tau would be our new equation, and that would just be cosine of, instead of t, 2 pi tau, and sine of 2 pi tau. Okay, so this is one way to do a general change. They would probably indicate what kind of change to make. All right, so far you should be able to find an easy arc length relationship, especially with circles. Obviously, what happens if it's not a circle? We're going to talk about that. If you're given a specific parameter to use that would vary as the initial parameter varies, you would approach it as a general change and just follow this. Okay. Any questions on either of those? Okay. Let's quickly talk about the chain rule, and then we'll talk about putting everything together. Okay, so we'll just kind of abbreviate this. R of t is a vector-valued function. It's differentiable. If g of tau equals t, there's a change in parameter. And again, g is also differentiable. So we have a vector-valued function that's differentiable. We're using a new general change in parameter function, which is also going to be differentiable with respect to its variable tau. Then r of g of tau is also differentiable with respect to its new variable, which is tau. And if we had to find the derivative of dr, well, find dr d tau, we have a couple of options. We could use the chain rule. And if you remembered it from last year, you probably can fill in the blanks here. What would I multiply dr dt with to get dr d tau? D. Yep. Okay. So here's an example. I want you guys to try both ways using the chain rule, and then also just by... There's two ways to do it. You can use the chain rule to find the derivative, and of course you could actually just plug everything in and then differentiate, so that's the other option. But go ahead and try it both ways. So let's say r is equal to I plus t squared j plus tk, and t is equal to tau cubed. What is dr d tau? Okay, so we have a vector valued function. We're going to change the parameter to tau. T is related to tau, as indicated here. Go ahead and find what the derivative with respect to tau would be when you change the parameter. So this, forget that this is a vector, right? So this is actually that's your J component, right? And this is your K component. So if you're going to write it in that, you should have J and K. And then the final step is now, so you can replace T so that everything is with tau. Does that make sense? Yeah, your final answer should all be in terms of just tau once you're done. So we know dr d tau is going to be dr dt times dt d tau. So if you find the derivative of r with respect to t, that'll be 0, 2t, and 1. The derivative of t with respect to tau would be what? 3 tau squared. So then we get 0, 2t times 3 tau squared, 3 tau squared. And the final step, since we know t is exactly tau cubed, you can replace t with tau cubed, so it'll be 2 times 3, which is 6, and then tau to the 5th power, and then 3 tau squared is already good. Okay, so that would be using the chain rule. I mean, it's not too bad. Depending on how these vector-valued functions look, one might be faster than the other. In this case, if you just do the substitution first, so go ahead and figure out r of g of tau. Then that would just be 1. T squared, if you square both sides, will give you tau to the 6. And then here t is exactly the k component, so that'll be tau cubed. And now if we differentiate with respect to tau, we still get 0, 6 tau to the 5th, and 3 tau squared. Okay, so either way, you get the same answer. Okay? Are there any questions on any of these little details? Okay. So probably the most important part of this whole section is what we're going to talk about now. Okay? So not to say that what we haven't done isn't important, but this is certainly going to be used not only in this unit, but probably later on as well as we introduce new topics. Okay, so finding an arc length parameterization. You know what, let me just start in a new page. Okay, so we've seen a very specific case of, oh, well, here we can bring in arc length because it's a circle and we know how that's related to this current parameter. But now we want to find a way, in general, for any curve, circle, line, cubic, any curve in 2 or 3 space, we should be able to bring in the arc length parameter, and here's how it would work. Okay, so let C be the graph of a vector-valued function, a smooth vector-valued function, r of t, and r of t naught, any point on the curve C. A positive change in parameter from excuse me, t to s, so current parameter, s is always going to be arc length parameter. Maybe I'll write that in. This is arc length. Having r of t naught as a reference point, is going to be what? You probably already know. We've talked about arc length with a specific case with the circle. Have we talked about how to find arc length? What's the formula? Integral of the magnitude of... Yes, very good. So now what we're going to do here, we're going to change the notation a little bit, and you'll see why. So we do want to have magnitude of r prime. I'm going to use u as the variable instead of t there. Reason being, we're going to integrate from initial point, or whatever value gives us the initial point, which is t naught, to t. Okay? So in the end, when we find the relationship between arc length and our vector-valued function, we're going to be left with the function in terms of t on the right side. That function in terms of t will equal s, and then you could manipulate it to figure out what you need to do. Does that make sense? Okay. So here's a pretty straightforward example. Find an arc length parameterization for r equal to cosine ti plus sine tj plus tk with reference point 1, 0, 0 and same orientation. Okay, so again, we're going to start by letting t equal u for a moment. Okay, so that r is going to be cosine u, sine u, and u, so that there's no confusion with variables. Otherwise, we're going to have an integral with respect to t. We're plugging in t values. It doesn't make sense if we do it that way. Okay, so let's find the derivative. The derivative here would be what? Yes. And let's see, what else do we need? We need the magnitude. So let's go ahead and find that. Magnitude would be square root of sine squared u plus cosine squared u plus 1. So in other words, that's the same as root 2. Okay, so now here's where we put everything together. So that means the arc length will be the integral of root 2 du. Okay, we're going to integrate from an initial value of t to t. We just have to figure out what this initial value is here. What is it? How do you know it's 0? Right, so if you go back to the vector valued function, if you plug 0 in for t, that's exactly how you would get this location, 1, 0, 0, right? Okay, so if we go ahead and integrate, we get root 2 evaluated from 0 to t, so that'll just be root 2 times t is equal to s. Okay, so here's the key. S, arc length, equals just root 2 times our original parameter t. Okay, so that means that t would be s over root 2. And now we can change the parameter on our original function. So we have r of s is going to be cosine of s over root 2, sine of s over root 2, and s over root 2. Okay, and again, one of the points of changing a function to an arc length parameter is now we can answer questions like this one. What are the coordinates of the final point starting at 1, 0, 0 that is 10 units away along the curve. Okay, so we talked about this a little bit on Friday before we left for the weekend. There's a very easy way to do this, right? So if I start, by the way, what shape was this? You guys remember? Just a helix, right? We've seen that a few times now. So the question is, starting at 1, 0, 0, where do I end up so that I have traveled 10 units along the helix, right? How do I figure that out? Yes? Plug in S equals 10. Actually, that's all you have to do. Right? So, since we know our arc length parameter represents exactly traveling 10 units along the curve, if I plug 10 into, not the original, but into our arc length parameterization, that's exactly what's going to happen. So if we do R of 10, that'll be 10, or I'm sorry, cosine of 10 over root 2. If you have calculators, I could use the help. Sine of 10 over root 2, and then 10 over root 2. So what vector, again, we get a vector from this function, but the components would be the same coordinates for our point, right? What's cosine of 10 over root 2 going to be? I'm going to go with something between 0 and 1. Same with sine. This is 10 divided by 1.4. Okay, come on, guys.
0.705
Thank you. 10 over root 2 is about, I'm guessing, 7 point something? 7.27? 0.7. Thank you. Okay? So, plugging in 10 spits out a vector, starting at the origin, ends up somewhere up there, but the coordinates are the same. Okay? And please be very careful when you write your answer. If I ask you where or what point we're at, make sure you write it as a coordinate, an ordered triple, instead of a vector. Okay? Okay, almost done. Let's try one more. Find an arc length parameterization for the line R equals R naught plus TV with reference point, again, R of T naught. So in other words, T equals 0. Okay, we'll go through this quickly. So S will be the integral from 0 to T. Okay, keep in mind, just think of this as R equals R naught plus UV, right? What is R prime going to be? Instead of with respect to t, now we are differentiating with respect to u. So we get v. Okay? So in here, we have magnitude of v du. Since we're doing a general problem here, we'll just keep going. This will be root v times u, evaluated from 0 to t. In other words, magnitude v times t is s. So t is just going to be s over the magnitude of v. So for any line, that's kind of why I did it this way. You can either memorize, this is the way to go, or you can kind of do what we did in the previous example. Just go ahead and take the line, figure out piece by piece, and then plug everything in. But maybe you can memorize this. I don't know. It's not too bad. You'll see this quite a bit. So our parameterization would then be r equals r naught plus s times v over v, if you kind of group things together. In other words, it's r naught plus s times a unit vector in the direction of the line. Okay? I think we can skip this example. Let's just finish things up here. 3 very important properties or theorems that we will make use of. Okay. First property. If C is a smooth vector-valued function with T as the parameter, as a general parameter, and S as the arc length parameter, defined by the formula we just talked about. S equals the integral from initial value of t to t of the magnitude of dr du with respect to u. So these are the assumptions for this property. We start with the smooth vector-valued function. Our arc length parameter s is defined by the usual. Then for every value of t, the magnitude of dr dt is going to be ds dt. In other words, the length of our tangent vector will be exactly the same as ds dt. Okay? Second one, same assumptions. Then we have dr ds, the magnitude, is going to equal 1. Third one. If C, same things as before, okay, and if dr dt, the magnitude of that, is 1 for all t, then for any value t naught, the parameter s equals t minus t naught is an arc length parameter that has reference point at the point on C where t and t naught are the same value. Okay, so these three properties are some properties as a consequence of the arc length parameter. The most important ones I can tell you right now are the first two. Okay, so we'll reference those later on. I can prove one of them. We have a couple minutes. Let's talk about A. Okay. This is one that you could expect to see. It's not too hard. So let's just start with what we know. Arc length is the integral of the magnitude of the derivative of r. So all I'm looking at is here's where I'm starting, here's where I want to end up, right? So I have s, I want ds dt. If I have s and I want ds dt, then what could I do to both sides? Yeah, just apply d dt. So now we have ds dt. And by the fundamental theorem of calculus, we just get magnitude of dr dt on this side. Right? Taking the derivative of the integral, we'll cancel it out. And now you're just left with the proper variable that we are integrating or plugging into the integral. Okay, so that's the first one. Maybe you can try the second one. Okay. I'm done. We are done with 12.3.